Hi guys, good morning, and I hope you guys are ready to celebrate because this is your last math lesson of third grade. So yay, that's pretty exciting, right? You guys have gotten through all of the content material, and so first, before we get started, go ahead and raise your right hand, bend it at 90 degrees at the elbow, and give yourselves a pat on the back. So we are going to be tackling lesson 33 today, and I think you guys will be excited because not only is it our last lesson of third grade, but it also is a pretty short and sweet one. So we're going to be talking about dividing shapes into equal parts with equal areas. And specifically, we're going to be really focusing on rectangles for this. So in your instruction books, you're going to turn to page 346. And we'll just jump right in. The question says, students at Memorial School painted square tiles. The tiles are put together to make designs on the office walls. Each design is a rectangle made from 12 tiles. What are some different rectangles that can be made using the 12 tiles? So A says, what if you put the tiles in rows that have 3 tiles? How many rows could you make with 12 tiles? So they're saying you're going to have a starting row that looks like this. Now, I know that this is only 3 tiles, so I would just keep adding rows of 3 until I get to 12. So if I added another row of 3, that would make it 6. If I added another row of 3, that would make it 9. And one more row of 3 would make it 12. So we had 1, 2, 3, 4 rows of 3 tiles. We would have all 12 tiles. So the question says, how many rows could you make with 12 tiles? You can make 4 rows. And then below that it says, draw squares in this rectangle to show what this looks like. So you should get something that looks similar to this, in that you have 3 in each row and you have 4 rows of 3. All right, B says, imagine you turn the rectangle on its side. So instead of like this, we would have something like this. So now, instead of having a row of 3 squares, I have a row of 4 squares. So it says, now how many rows does the rectangle have? So I would have 1, 2, 3 rows. And how many tiles are in each row? Now I have 1, 2, 3, 4. Draw squares in this rectangle to show what it looks like. So something similar to this in the blank space to the right. C says there are other ways to make rectangles with 12 squares. Explain how you would find other ways. On a separate piece of paper, make drawings to show what the rectangles look like. You can certainly go ahead and do that if you would like. I would like you to think about what are some other ways to make a rectangle with 12 squares. You could draw them if you would like, but it's not a requirement. I want us to first of all go ahead and think about what does this remind us of. And hopefully it will remind you a little bit of either area that we've worked with, where we're creating a grid and we're counting up the numbers of squares, or it may even make you think of an array as a strategy for solving a multiplication problem. But in both of those, you are having a multiplication equation. So for area, remember, the area of a rectangle is length multiplied by width. If you're finding an array, you would have one side multiplied by the other side. So in the 2 cases that we just had, if I turn my rectangle like this, I would have a row of 3, and I would have times 4. Right? Because I have that row of 3, 1, 2, 3, 4 times to get 12. So that's one way of showing how the rectangles are displayed. But then remember, we also tilted it like this. I didn't change the number of squares, but I did change the orientation. So I have a different array. I have a different grid here. This and this are really similar, but because the orientation is different, they're actually saying different things. So now I'm going to use the same numbers because, again, I didn't change how my rectangle is constructed. But instead of having rows of 3 squares, I have rows of 4 squares, and I have that 1, 2, 3 times. So we see that commutative property of multiplication in that order doesn't matter. Remember, we can flip-flop and we get the same answer. So before we had 3 times 4 equals 12, and here we have 4 times 3 equals 12. So it is getting us the same answer, but we're changing the order around. We're changing how our rectangle is oriented. So I want to be clear that even though we're getting the same answer and it is showing that commutative property, we still have 2 different arrays, 2 different rectangles. So getting back to C, if we were to think about some other ways that we could make rectangles, let's think about some other ways that we could multiply to find 12. So we have 3 times 4 equals 12. And then we have its flip-flop, 4 times 3 also equals 12. Now what I do when I'm trying to find factor pairs, remember we have factor times factor equals product. So when I'm trying to find factor pairs, meaning 2 factors that will equal the same number, I usually start with counting numbers and I go through until I get to the product. So in this case, our product is 12. So I'm going to start with 1 and continue on until I get to 12 and see if there's any other pairs in there. So we know with multiplication that there's also the identity property that says any number times 1 is itself. So I could have 1 times 12 to still equal 12. So that would be 1 row with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 squares in it. So that would be one way. And now let's remember that we can also switch it around. And so I could also have 12 rows, each with 1 square in it. So I could have my flip-flop of 1 times 12 would be 12 times 1. Okay? So that's another 2 ways to show different rectangles that would display 12 squares. Let's keep going. So I started with 1, so now I'm going to count on to 2. So I have 2 times what would equal 12? Well, I know my doubles facts, and so I know that 6 plus 6 is like 6 2 times 6 plus 6 is 12. Therefore, 2 times 6, or 6 2 times, would equal 12. So I just said that in the reverse way. I really thought of it as 6 times 2. But because order doesn't matter when we multiply, 2 times 6 and 6 times 2 would both be factor pairs. A 2 times 6, a 2 by 6 rectangle would look like this. I have 2 in each row, and I have 6 rows. But then 6 times 2, I would have 6 in each row and 2 rows. So again, the numbers that we're using, they would be like in a fact family. They both equal 12. So we're still using 12 tiles. But the way we orient it, the shape of our rectangle is going to depend on the order. So order doesn't matter when we multiply when we're finding the product, but it does kind of matter when we are talking about orientation of our rectangles. All right, so 2 and 6 and 6 and 2 would be another option. Okay, 3, oh, we already have 3, and we have 4. So 3 times 4 is 12, and 4 times 3 is 12. So now I'm going to keep counting. 5 times, nothing times 5 gets to 12, so that doesn't work. 6, we already did that, so 6 times 2 equals 12. 7, nothing multiplied by 7 is going to make 12. 8, same thing. 9, same thing. 10, same thing. 11, same thing. 12, oh, and here we have it, 12 times 1. So we have come up with all of the factor pairs that could make 12. So this is it. This is the definitive list. These are the only ways that we could make our arrays of rectangles to show 12 squares. But you'll notice that we have 1, 2, 3, 4, 5, 6 separate pairs. So getting back to C, it says there are other ways to make rectangles with 12 squares. Explain how you would find the other ways. Well, you could think about what numbers multiplied together would equal 12. This follow-up part of that question is on a separate piece of paper, make drawings to show what the rectangles look like. Again, you can do that, but it's optional. All right, moving on to the next page on 347, it says, on the previous page, you formed different rectangles using same-sized squares. You can also break apart a rectangle to show parts that are all the same size. So this should harken back to fractions when we are taking a whole, like a whole candy bar, and we're dividing it into equal parts. So in this case, I divided mine into 1, 2, 3, 4, 5, 6 equal parts, right? If I cut it in half, I would have a way to show 12 that may not be necessarily equal size squares. So when we are breaking apart a shape into equal pieces, we want to make sure, again, that our that our pieces are approximately equal. So we're not going to take the time to measure each one, but we want them to look pretty much equal. If I were to divide my rectangle like this, we could see that I have 3 different sizes of triangles, rather. So these would not be equal parts, so this would not be a way that I could divide my rectangle into thirds because it does not show equal parts. If I wanted to show 3 equal parts of my rectangle, a better way would be to do something like this, where they look approximately equal, or I could also go like this. So there's different ways that we can divide up our rectangles, but it is important that we are dividing them up into equal parts. Now, below, it says the shaded parts of each rectangle below cover 1/4 of the whole area of the rectangle. So this gets into when we were talking about equivalent fractions. So for example, actually, I'm going to erase this. So the first picture shows you a rectangle that's cut into fourths like this. And so we would see that we have 1, 2, 3, 4 pieces. And if I took 1 out of those 4 pieces and shaded it in, I would be showing 1/4. But I could also cut each of those pieces in half. I'm still showing 1/4 overall, but if I were to count the fractions, I would have 1, 2, 3, 4, 5, 6, 7, 8 total pieces, and I would have 2 of those 8s. So 2 8s would be the same as 1/4 of my shape. Let's do one more. Let's say I have a rectangle and I cut it into fourths this way. We know that if I shade in 1 of those pieces, I would shade in 1/4. But instead of having 4 equal pieces, I'm now going to go ahead and cut each of those pieces in half for a total of 8 equal pieces now. So if I still wanted to show 1/4 of it, I would still shade in the same amount of space, but notice that I'm shading in 2 of the 8s instead of just 1 of the 4ths, but it's showing the same amount. So 2 8s again is equal to 1/4. Those are equivalent fractions. They have the same value. Below the second set of squares, it says all shaded areas are equal in size, even though the shapes of the parts and the number of parts are different. So I can show 1/4 this way. I can show it this way. I can show it this way. So even though in this one, it's like my 1/4 is stretched out, it still shows the same amount of the rectangle. If there is more than one part shaded, the shaded parts do not need to be next to each other. So for example, if I showed 1/4 this way, I could show 2/4 like this. So they're not touching, but I still see that I have 1/4 and 2/4 over here. I'm still showing 2/4 of the rectangle as being shaded. If we were to think of it like circles, because I always like circles when I'm dealing with fractions, I have 1/4 shaded right here. If I added in this piece, I would have 2/4 that are shaded, but it doesn't just have to be that 1/4. I could also have this piece that's shaded to show 2/4, or I could even do this one and it would still show 2/4. So they just want you to get the idea that when you have equal parts, you can combine them in different ways to show the same thing. All right, so question 1 at the bottom says, if you divide a rectangle into 6 same-size squares, are the areas of the squares equal? So let's just stop there for a second. And I'm going to draw a rectangle with approximately same-sized rectangle pieces. So they're saying if you divide a rectangle into 6 same-sized squares, are the areas of the squares the same? Well, the key word here is same size. So if I were to take this piece off, and if I were to lay it over the top of this piece, use your imaginations, it would perfectly cover that piece, right? And I could do that with all of the other pieces because they're all the same size. So would they have the same area? Yes, because they have the same size. They cover the same amount of space. So now if I were to do that closer to what the problem is asking and take a rectangle and divide it into 6 same-size squares. Yeah. There we go. Again, my picture isn't perfect, but we can imagine that if I'm cutting them into equal pieces, yes, all of the squares are going to be the same size. Remember, we talked about in fractions, if you have a candy bar and you're breaking off pieces and you give one little tiny piece to your friend and you take a really big piece, they're not equal. And so it's hard to compare. You can't say that everyone is getting the same amount when you don't have equal pieces. If you do have equal pieces, though, you can compare. And so that's what this is saying is, if you have all the same size pieces, then yes, they all have the same area. The second part of that question says, what do you know about the area of each square compared to the area of the whole triangle? Well, if you cut it into 6 same-size squares, each square would represent 1 out of the 6 total pieces, right? We remember that from fractions. So this would be 1/6. This would also be 1/6. This would be 1/6. This would be 1/6. This would be 1/6. And this would also be 1/6. So each of them would have a value of 1/6. We call that unit fractions. So any fraction that has 1 as the numerator is a unit fraction. And so each of these squares would have a value of 1/6 of the total rectangle. So it wouldn't matter if I shaded in this 1/6 or this 1/6 or this 1/6. They would all have the same value of 1/6. If I added them all together, if I shaded in this one and this one and this one, it would be like adding my fractions. I would have 1 and 1 and 1/6, 1/6, 2/6, 3/6. Okay. let's go ahead and move on. Turn the page, if you would be so kind, to page 348. And the problem tells us that Brett's art teacher asked him to fold a sheet of paper 4 times and then color 1/4 of his paper red. His folds are shown below. How could Brett color his paper? So I've taken a piece of paper and I've folded it in the same way that is shown in the picture. So first of all, I'm taking the paper and I'm folding it in half once, then I'm folding it in half again, then I'm folding it in half again, and then I'm folding it in half again. So when I open it all up, you can see that I have created the boundaries of all these little rectangles that make up my piece of paper. Now, in order to figure out how many we need to color to show 1/4 of the paper, we would need to figure out, well, we could do it 2 ways. We could think about what 1/4 of the paper would be, or we could count how many squares. So I'm going to start with counting squares because that's going to be the most accurate measure first. So I know that I have 1, 2, 3, 4 squares in a row, and I have 1, 2, 3, 4 rows. So I would have a rectangle that is broken into 4 by 4 pieces, or we know that 4 times 4 equals 16. So I have 16 equal pieces that my paper has been divided into. So now I would need to think about what 1/4 of that would be. Well, I know that I have 4 rows of 4. So if I colored in one entire row, I would have 1 of the 4 rows colored in. I could do it the same way with columns. I could think of, I have 4 equal columns. If I colored in 1 column, I would also have I would have 1/4 of the columns. You can also kind of see that there, I'm going to go ahead and draw it on here. If I were to think about my rectangle in what we would call quadrants, so 4 pieces, quad, like a quad bike, has 4 wheels. So this has 4 sections, right? And again, each section has 1, 2, 3, 4 squares. So whether I did it as a row of 4 squares, or a column of 4 squares, or a quadrant of 4 squares, each time I'm coloring in 4 squares to get 1/4 of my total paper. 1/4 of the 16 pieces would be 4 pieces, right? So, so we're actually going to go ahead and skip on over to the questions on page 349. So how many rows are on Brett's paper? So again, let's think of if we folded it and folded it and folded it and folded it. When we open it up, we would have 1, 2, 3, 4 rows. Number 3 says Brett colors 1 row of his paper. What fraction of the whole paper is 1 row? Explain. So I'm just going to go ahead and do that. If I color in 1 row, I've colored in 4 squares, but I've colored in 1 of the 4 rows, right? So there are 4 rows. So I've colored in 1 of the 1/4 of the rows, 1/4 of the paper. How much, what fraction of the whole paper is 1 row? 1/4. And explain, there's 4 equal rows. And so 1 out of the 4 rows would be equivalent to 1/4 of the page. Number 4 says, did Brett color 1/4 of the paper? Sure did. Number 5, how else could Brett have colored 1/4 of the paper? So we talked also about, remember, orientation matters when we're talking about our rectangles. So if I still had 1/4, I could think of it as 1/4 of our columns. So he could color in one column and it would still be 1/4. We also talked about quadrants. If he just colored in 4 squares, no matter where they were on his paper, if they're grouped together like this, or even if he spread them out, he would still have 1/4 of his paper colored. So he needs to color in 4 of the 16 squares to color in 1/4 of his paper. Number 6 says, to color 1/4 of the paper red, does Brett have to color 4 parts that are next to each other? No, he doesn't. So as we just talked about, he could choose any 4 pieces and it would still represent 1/4 of his paper. All right, moving on to numbers 7 and 8 at the bottom. So number 7 says, divide this rectangle into 8 equal parts. So they have given you, they have drawn the outline of a rectangle, such as this, and they want you to divide it into 8 equal parts. So there's a couple ways that you could do this. You could think of it as 2 rows of 4 squares, or you could think of it as 8, 1, 2, 3, 4, 5, 6, 7, 8, 9, whoops. Thought I got a little carried away there. So you could also think of it as 8 equal pieces shown like this. So how you do it is up to you, but it says divide this rectangle into 8 equal parts. What fraction of the whole rectangle is each part? Well, if we had 1 of these shaded in, it would be 1 out of the 8 total parts, so you would have 1/8 of the whole. Number 8 says draw the rectangle from problem 7, so they're asking you to draw the rectangle again. Show a different way to divide it into 8 equal parts. So if you did it this way, do it a different way. Okay. And then it says what fraction of the whole rectangle is each part? Well, doesn't matter how we cut it up, we still have 1 out of 8 total parts. So each part would still be 1/8 of the total rectangle. And that, my friends, is the lesson. That is all of lesson 33. It's hard to believe, I know, because it seems like pretty simple stuff that we've already covered before in different chapters, but so important that they feel that you have to cover it again in different words. But you're done. You made it to the end. So the practice pages that you have with this lesson are pages 367 and 368. That's 1 double-sided page, and 369 and 370. That's 2 double-sided, or together that would be 2 double-sided pages. And then you are done. Please send me pictures of your completed math work. I will send you stickers. If you would like to do the performance task, that comes at the end of your math lesson, that would be awesome practice. I'm not going to require it, but I do think that the more we practice doing those, the better we get at them. If you do decide to do that, please email me a picture or mail it to me in the mail so that I can give you something special for taking the extra time to do that. Congratulations, you've made it to the last math lesson. Please feel free to go out and celebrate how you see fit, and I will see you at the Google Hangouts. All right, bye guys.